Okay, so welcome everybody to tonight's meeting, and we'll go through a little bit of an agenda first of all of what we're going to do tonight. Okay, so tonight's notices. First, we're going to have a few notices that I'll tell you about, and then we'll move on to Len, who's going to take us up with a news item, a topical item. And then we'll have the main presentation from Richard, followed by Richard, who's going to give us a tour of the night sky. And then we'll need the refreshments after all of that. And anyway, we'll press on and do as quickly as we can. Got to do the safety notices, fire exits, left and right. And at the back, the door you come in, the toilets are at the rear and by the entrance where you come in. And we are recording this event as well. So those on Zoom as well, be aware of that. Quick note about the Southwest Arts Astronomical Society for the visitors that are here tonight. We're founded in 1968, so we're over 50 years old, and we currently have about 158 members. Seems to be gradually growing, which is very nice. We do our monthly meetings. They normally run from September to May. We have a 3-month break in the summertime because it's really difficult to get speakers to fill those gaps. And it's usually the last Friday of the month, but not always. So, for example, at Christmas time, it gets shifted because of requirements that the school need to use certain halls here. So we come a little bit earlier, for example, and of course, when Easter falls and so on. We do have our own observatory at London, which I'll tell you about in a moment. And we do have access to the planetarium here at the RMS. Unfortunately, it's been in a state of disrepair for a while, and we haven't been able to gain access to check exactly if it's operable or not. So Richard and I will do that one of these days when we get a chance. But in the meantime, we'll carry on with doing Stellarium here. And by the way, Stellarium is a free program that you can download onto your own computer. It's a very useful program as well for finding objects in the night sky. We do send out an occasional newsletter. We stopped doing it monthly because we were discovering that people didn't actually read it all. So we send out emails instead that contain news items or information. Subscriptions, for those that are not aware, it's £16 for an individual, family £24. It can be a family of 2, 4, 6. We're not really fussed. The more younger people, the better. We'd really like to encourage younger members to take an interest in astronomy. And of course, our website, SWHAS.org. Bit more about this site for the people that are here for the first time. You came in at the main entrance, which is here at the bottom of the screen. Our target destination is the Cadogan House Hall. And under normal circumstances, you can go through the barrier, through the gates, and up through the Central Avenue to park up here. These gates have been problematic. They were at the last meeting, as you might remember. They're still continuing. They don't seem to have remedied the situation. Tonight, because I had a lot of equipment to carry up here, the security guard let me in, but he had to manually pull the gates open, and it wasn't an easy task, I can tell you. Yeah, just another few things about the site. There is an observatory here on the right-hand side of the site. It's on top of the science block, and there is the planetarium just beside it. Okay, so on occasions, we're required to use this new Mark Hall, which is here in the center, and that's directly opposite the main car park. It's much easier to access. We used to use that as a site for our talks, but we got moved over here because they were using that more frequently. And it's also the point where they've got their reception for people visiting the site. So they really want to keep us away from that if possible. So our own observing site is at Flondon, which is about 6 miles from here. And this is a Google aerial image of the site. And on the site, we've got the observatory and we've got the hut. Hut's very important, especially in winter months when it gets cold. And here's just a couple of shots of what it looks like. We've got an 11-inch Celestron C11 on an EQ8 mount. There's a picture of the dome, nice and clean. And to find it, you search for SWHAS Observatory on Google Maps, and it will find it for you. And that way, from your current location, you can easily get directions to get there. Okay. We did something just earlier in the week, Tuesday, the 25th of October, we did a partial solar eclipse session in Castleberry Park. And here you can see a setup with our Celestron 6-inch with the filter on it, and then Pete and Bernice's solar scope. And the idea was that we would observe the eclipse. And we got a few shots. And unfortunately, I didn't bring a proper camera with me. I just used my phone. So these are phone shots. So here you can see them looking at the sun. And this is what we saw just as the eclipse started. This is in the white light. And if you look very carefully, there are sunspots here and here. Just mark those. And as the moon comes in, actually, one of the things that I was quite surprised to see was ragged edges of the moon. I was expecting to be quite crisp, but these, of course, are the craters of the moon that are blocking out the eclipse. And this is a little bit further on, when it was reaching maximum. And again, you can see the ridges here. And if you look, you can still see the sunspots. And if I zoom into that area there, you can actually see it's quite ragged. You can see the edges. Bear in mind, this is a phone shot held up to the eyepiece of the lens of the telescope. So it's not entirely a very good way of doing it, but under the circumstances, we thought it gets a few things. Doing the same with looking through the hydrogen alpha scope, you can see it's very red. But the interesting thing here is we can see the prominences and solar flares sticking out as well of the eclipse. The flaring here is due to reflections between the camera and looking through the lens. It's not a very scientific way to do it, but if you look at that there, you can quite clearly see these loops. And these are pretty big loops. These are extending, like 50,000 miles into space. So to catch that on a little phone camera, I thought was actually not too bad at all under the circumstances. So just a quick bit about our upcoming events. Our next workshop is going to be a telescope workshop here. And the idea is that if you've got a telescope that you want us to guide you through setting it up or correcting it, if there's something wrong with it, we'll try and do our best to do that. I think I have to make a caveat at this point in time. If the gate is still broken, it's highly unlikely we'll be able to conduct this workshop. So I'll have to scratch my head and come up with something else in place. So I'll send out an email confirming that we will have access. We'll also show you different types of telescopes. So we'll do a little introductory bit about telling you the different types of telescopes, what you can use them for, what is the right type of telescope for you, and so on. And then you'll be able to make some choices. And also take the opportunity to remind you that the Society owns probably 8 or 10 different telescopes of various shapes and sizes. And these are available to members to borrow and take home and try. And we would encourage you to do that, because spending several £100s on a small telescope or several £1,000s on a big telescope, it's a big outlay. And don't do that until you've looked at that, because you might find at the end of the day, a pair of binoculars are just going to be as good for you. It depends on what your aim is to do, whether it's deep sky observing or astrophotography. We'll tell you all about that as well in this workshop. So then December the 16th, not the last Friday of December, but right in the middle, it's our members' images, bring and buy, and Christmas festivities. So we'll have lots of fun there. So our next meeting is going to be the telescope workshop. I've already told you about that. So I think I'll go on to Len at this point in time. And if Len wouldn't mind coming up, and I'll get him started.
Okay, well, I'm going to say a few words about the DART asteroid mission. I know it's been covered extensively in the press. However, there's a couple of aspects I found interesting, which you may not have heard about. So firstly, let's recap what it's all about. So the Earth's under constant threat of being hit by an asteroid or comet. We know it's something that happens regularly, and sometimes it can devastate the Earth, like 65 million years ago when the dinosaurs were wiped out. However, these days, it's just possible that we could do something about it. We are able to track larger objects, and it might be possible to divert them so they miss the Earth. So DART was actually an experiment to see if this could work. DART was launched in November 21, and it headed for the asteroid Dimorphos, which is in orbit of a larger asteroid called Didymos. DART first orbited the Sun before it collided with Didymos on the 26th of September, just gone. As the craft impacted Didymos, it changed the trajectory of Dimorphos, and therefore its orbital period around Didymos. You get the impression that we can see these asteroids clearly from Earth, but we can't. The only reason we knew that Didymos existed is that the Dimorphos existed was because the light from Didymos dimmed every 12 hours or so. And therefore we knew it had a small asteroid. So in fact, the only measurement we can make from Earth is the change in the orbital period. A 1% change was expected, and the original orbital period was 11 hours and 55 minutes, and it was expected that that should reduce by 10 to 20 minutes after the collision. It's a clever idea, because if we tried to alter the trajectory of an asteroid orbiting the Sun this way, the change would be so insignificant we wouldn't be able to detect it, especially as other factors like pressure from the solar wind, etc. We just wouldn't be able to take a measurement. So it's a clever idea. And the gravity holding Dimorphos in place is really weak and therefore sensitive to small changes. Well, it worked. Dark did collide with Dimorphos, and the collision was recorded in several ways. Firstly, DART itself took pictures right up to the point of its collision. And 10 hours previous to the collision, DART released a small craft called Lichia Cube, I think it's pronounced, which recorded the impact and sent pictures back to Earth. And finally, Earth-based telescopes and spaceborne telescopes were able to record the impact. So firstly, let's look at the pictures from DART itself. So up on the top left here is the first picture where both asteroids were shown together. And then we come along and we can see just Dimorphos alone. We passed Didymos at this stage. Then down here, Dimorphos starts to get bigger. And then the last few pictures were where Dimorphos took up the whole of the frame. This one on the bottom left being the last main picture. Whoops. And this last picture was interesting. Well, I'm finding that way. I find it interesting. It took a complete picture of the asteroid, but then it crashed into the asteroid while it was sending it back. So that complete picture existed in the memory of the spacecraft, but then it would never be seen and was obviously destroyed. So the collision itself, this is an artist's impression of what they thought would happen. The spacecraft would make a nice little crater, and if we were lucky, we might see the debris cloud coming away from the asteroid. This is one of several artist's impressions, the only one I could find actually. And they all show a little crater, bearing in mind this orbiting asteroid is about the size of a football stadium. So a nice little crater with stuff coming back. Well, that's what they thought would happen. This is what actually happened. So this is a picture from Lichia Cube, and you can see that the light from the collision makes it nearly as bright as the main asteroid. So it really was a massive, much more than expected collision. And yes, it was an incredible. It's also incredible that it actually worked. When you think they were sending the spacecraft to an orbiting asteroid which couldn't actually be resolved from Earth, it was an amazing achievement. I think we sort of come to expect now, haven't we, that these missions are so good and perfect, and they usually are, but it was an amazing achievement. So next, the Hubble took a picture, and you could see this huge tail caused by the collision. What you're seeing is the light from Didymos. Obviously, it can't resolve Dimorphos, but the light from the tail is extensive. It's enormous, in fact. The overall light from the asteroid system increased 3 times for more than 8 hours. So it was a major event. Similarly, this is a picture from SWHAS, SOAR telescope in Chile. And you can see that the vast plume of dust and debris, more than 10,000 kilometers long, and the ejector has been pushed away by the sun's radiation pressure, not unlike a comet. Basically, that's the first item of interest. The collision was much more spectacular than predicted. This is my last slide. So did it actually work? Well, there were three possible scenarios of what could happen. Firstly, on the left here, it could have hit a very solid asteroid, and it would have basically flattened itself on the asteroid. But in that case, it would have transferred its energy and it would have changed the orbit. The second possibility is what actually happened. It will make a crater in the comet, will have ejecta, and the ejecta will go in the opposite direction of the original spacecraft, and it will impart its energy into the asteroid. Finally, it was possible that it would have met an asteroid which was quite low in density, and the spacecraft would have gone through and there would have been an ejecta on the other side. In that case, it wouldn't have imparted its full energy. So it's just as well that it did what it did. Yes, so we were expecting a change of 10 to 20 minutes in orbital period. That's quite a large spread, considering we knew the mass and speed of the spacecraft, we knew the mass of Dimorphos. I thought when I very first saw this, that's quite a wide spread. And perhaps they were thinking that it might burst through. So that's why the last spread was there. But we didn't get that. We got a change of 32 minutes. The original 11 hours, 55-minute period has changed to 11 hours, 23 minutes. So I guess that's very good news and that it worked. So, we may be able to use this for diverting asteroids in the future. But it was way beyond original estimates. So I don't know why that is. And I've been reading about this and looking for that information. All I can assume at the moment is that the original estimate was wrong, but I'm still looking for that information. But that was the second interesting thing I thought about the DART mission. But in any case, it shows that we can alter the trajectory of an asteroid should the need arise. We've just got to see it before it gets here, gets too close to us, then get a rocket to it with a large enough mass to divert it. I do hope that's possible. And that's the news.
Well, thanks very much for that, Ben. Yeah, very interesting. Well, that's certainly interesting to see the after effects of that. I know we've probably all seen bits and pieces on television, but as Len says, it's really reassuring to know that we can influence some of these potential end-of-life scenarios. Thanks for that, Len. So tonight's main presentation is Richard. He's going to talk to us about solar eclipses. So if I could ask Richard to come up.
Now, while Sean's doing that, just briefly, what I'm aiming to do is talk a little bit about the history of observing solar eclipses, a little bit of science, a little bit of history, and we'll have a little conversation afterwards about the is it really worth going and seeing them? Okay, I'll begin. So eclipses of the sun. Now we're educated, we're sophisticated after we've been around a awfully long time. So the eclipses of the sun have become something of a tourist attraction almost now. But right at the beginning of time, that wasn't necessarily the case. In the early days, when we go back to prehistory here, you've got to remember that these people that our ancestors, they knew nothing about what was going on in the sky. All they knew was that it got dark at night and it was light during the day. They had no way of understanding anything because it just happened. And you can't imagine how frightening that is. I sometimes hear people referring to the modern streetlights. So it's like the Blitz out there, you can't see anything. And of course you can, because we've got streetlights, but of course they're not as bright as the previous ones. So you've got to imagine then that when you stuffed out your candle and the little smoky bits had gone, that was it. You couldn't see anything. Imagine being in a dark room, and I have worked in a dark room, and I know darkness is palpable. You can feel it. It's very frightening in a sense if you don't know what you're to expect. So when it's all right at night, because this was kind of a regular thing that you could predict. And after a while, they must have got used to the fact that the bit gets dark, you just don't do anything. After all, you can't play with your computer games or read the paper or anything, and there's no electricity anyway, you can't see. So what do? You don't. The only thing you can do is to look out on night sky and make up stories about it, which is basically what they did. But when you think of people being settled in something like the Babylonia or whatever, the land of the two rivers, the Tigris and Euphrates, they were settled. They were farming people. They grew crops. So the sun going out is frightening. It's really scary, and we can't really appreciate what that's like, because we never experience those conditions now. We can't imagine what it's like, and suddenly see the sun disappearing was a major scare, because it might not come back. Eventually they got to figure out that it does eventually come back, and after a few minutes it's all returned to normal. But the effect on animals and the effect on the population was pretty devastating. Now, to see if I can move my image over a little bit. Can I over a little bit so that you can? I'm sure I can. Let's try again. See that? There we go. Put it down there for the moment. Over there. Okay, so I want to show you this picture. The first picture I want to show you is this one that I've just highlighted. Now, this was taken from the Golden Book of Astronomy, which is now a pretty old book, 1956. The reason I put it there is because I saw it in an article on eclipses many years ago by David Levy. And I knew where the illustration had come from, because for my 10th birthday, I had this book, the Golden Book of Astronomy, for my birthday. And it was really a great book. It covers the entire universe, as we knew it in 1956. A few changes now, I'm afraid. But it shows the effect that it had on people. And funny enough, when I was lucky enough to meet him, Jan and I met him and went to a place with a group from Sky and Telescope in 2003. And we had a chat about this. And I said, I recognise that picture. I've got that book. And he said, yes, Richard, I got that for my 10th birthday. And I said, snap. So we both had the same book. And strangely enough, his birthday is 11 days after mine. So that's just a coincidence. So I like that picture. I think it's rather good. It gives quite a lot of image of fear and scariness, and beat hammers and beat drums and make a lot of noise, which is what they did, trying to frighten the monster away. In India, pregnant ladies had to remain indoors during the whole eclipse, because it would have done something to them that was nasty. Seems a lot of things seem to involve women being inside. I don't quite know why. That's not the only thing. For men, the Ganges was a favourable site to be in because it was safe. Some form of Islam, it was forbidden to look at the obscure sun. And if I move this again, I'll move this down a little bit, up a little bit. Get out of the way. You can see that this is 2006, and this is in Libya, and the people are actually looking the opposite direction, which is something that we would never do. We would never do that. But that was part of Islamic belief. Germanic tribes thought an eclipse brought disease in the form of rain that was contaminated. Tahiti. Now, I read this story and I find it really strange because I can't understand it. But I quoted this. I looked it up. In Tahiti, the sun and moon are lovers. Their union creates the eclipse, but in that darkness they get lost, and they create stars so they can sail away again. It doesn't make a lot of sense. But sometimes eclipses actually did something on Earth that nobody else could do. For instance, the Lydians and the Medes stopped fighting in May the 28th, 585 BCE. They did. They signed a truce because they saw an eclipse. Mind you, they began to get a bit more worldly wise, and the late leader of Athens, named Pericles, in a siege battle of 430 BCE, the sailors started getting frightened by this eclipse taking place. So he held his cloak up and he said, well, it doesn't really matter. It's only the sun being covered. Are you more frightened by that than you are of my cloak? And they carried on. So by that time, eclipses were a little bit more understandable. So what advances could we have on eclipses? There we go. Right, the Babylonians. Now, the Babylonians were an amazing group of people. They were around a very long time, and they actually made cuneiform tablets of happenings in the heavens. They found patterns from them because they kept them over thousands of years. They were very good at analysing them. In fact, the best person to give this part of the talk will be Aristoconides, because he actually gave us a talk about the Babylonians when he was talking about the Antikythera machine. In actual fact, they uncovered an awful lot of patterns. They were very good at spotting these things. For instance, one of the things they did point out was the 8-year cycle of Venus, which is another thing that actually we know that the Aztecs did as well. But we only learned that recently. People often ask why we talk about the Babylonians, we don't talk about anyone else. That's because our whole history is based on Babylonian findings. The people in the Aztec people, we've only learned much more recently that they were doing advanced mathematics and astronomy. However, what they did do by creating these patterns, they realized that actually eclipses repeat over a period of years. That period is 18 years, 11 2/3 days. So it's actually a repeating period. It's not the exact same time of the day. It actually rotates around, moves around, so it's different longitude. But in actual fact, they do repeat. So in actual fact, they had a way of knowing how to predict eclipses, and that we call a SWHAS. Actually, that's not a good word to use. It really isn't. Because that's actually what they call the whole universe. We seem to have tied this up to this particular prediction. But by the golden days of the Greek civilization, it's possible to build a calculator. I know I still stand back in amazement at that. A calculator to work out future eclipses and other phenomena. The amazing Antikythera machine was a result. It was discovered off the coast of the island of Antikythera, which is just off the coast of Crete, a very tiny island, in the 1940s by sponge divers. And very carefully, they managed to alert the Greek authorities rather than the Turkish about this find, and so it actually found its way into the preservation, etc. And of course, is now being still worked on. So you've got an illustration there of the cuneiform tablet they used, and the ziggurat, which is often confused. It's often imagined that the Tower of Babel that's mentioned in the Old Testament is actually something that they did, because it was a temple as well. But the higher part of it was used to observe the heavens using measuring equipment. Now, you have to remember that what they're not trying to do is to predict eclipses and to actually solve the phenomena. They're not actually trying to find out what causes them. They're actually just really doing it because they want to know when the eclipse is, because for their astrology, so they know when to tell the ruler to hide somewhere. For instance, with lunar eclipses, if there was a lunar eclipse and Jupiter was in the sky, the king of Assyria was in danger. So what they did, they used to appoint a proxy, who was usually a prisoner, to make him king for a day, or how long the period was. And then they bump him off and bring him king back. The king was still working in incognito somewhere out of the city. So there were reasons for this. It wasn't that they were trying to understand it; they were just trying to predict it for other reasons. So then we come on to the moon's orbit. Now, the moon's orbit is very strange. It would be really easy if it just sat on the ecliptic and went round the Earth on the ecliptic, but it doesn't. In its very simplest form, it actually is inclined to the ecliptic by 5 degrees. If you imagine two hula hoops, where the one is put in the other and angled by 5 degrees, you can see there's 2 points where they cross. In fact, they're marked on here as a node. Node is simply a crossing point on which the moon is actually on the ecliptic. Now, eclipses can only happen when the moon is actually at a node. And so that limits them rather, because it's a matter of timing. So that these nodes actually, they precess, they move around, so that as the moon orbits the Earth, the node is progressively moving around. So when the node is and the moon when the node reaches the point that the sun is, then you're going to get an eclipse if the moon is new at that time. Now, in science, we always talk about the Copernican principle. That is that no matter that the Earth is not special, we are not special. Everything is to do with it is the same everywhere. It's not. We are not special. There's no special case for the Earth. When you look at this, you begin to wonder if that's really true, because there's such a lot of coincidences that it really is quite astonishing. The other fact, of course, is that the moon is 400 times smaller than the sun in reality, but it's 400 times closer. So that gives us a perfect view. I mean, they do fit remarkably well. Now, the moon and the sun are actually quite small in the sky. It's half a degree. When the first planetarium being set up in Jena or Jena in Germany by the SWHAS company, they did a test run with the first instrument with all of the staff, and they all looked at it and they made comments. And the one comment that kept coming out was, that moon's too small. And they said, no, it can't be. It's half a degree. We made sure it is. But they had to make it a full degree for it to look right. We imagine the moon bigger than it really is. And of course, when we see the moon low on the horizon, that's the moon illusion when it looks much bigger still. So, but you've got to see it from the point of view of that they are an amazing set of coincidences. I mean, they really are. It's astonishing. If you wanted to give a clue as to, finding out more about the sun by having it eclipsed, that would be a good way to do it. Also, the path of totality, and you can see this strip here, which shows the path. It can be huge. It can be thousands of miles long, but the width of the area of totality is very small. It's only 150 miles wide, and it sometimes isn't that. So you have to be in that small area to actually see the eclipse. So if we go on to the next. Again, I've gone back to this is Eclipse Tracks. I've gone back to that book of 1956 because there's one or two that are rather interesting here. One is this one here, February 15th, 1961. It went through Yugoslavia. We know it went through Yugoslavia because that was when it was observed by Patrick Moore from the top of a mountain. And that was the first television program that was recorded of a total eclipse, first by the BBC. It was several other observers. Colin Ronan was in Florence and so on. There were various other people observing. But there is another interesting fact about this eclipse. In 1962, a film came out directed by Richard Fleischman, and it was called Barabbas. Now, this was about Barabbas the thief and the crucifixion story of the Pilate offering Barabbas to be released, or Jesus, and they want Barabbas released. So the story is about Barabbas. But the director of the film, Richard Fleischman, he actually shot this part of the film, the actual crucifixion, as a total eclipse of the sun. It was that one that he used. So there's just an interesting thing, the side story. Two things happen with that particular eclipse. Now, Another one that was really quite famous was the one here. This one that's June the 30th, 1973. Now that one was observed by a lot of people on a boat called the Monte Umba, and most of them from the BAA. That was probably the biggest party they had, and it was an eclipse party. And I remember I was in the Florida Astronomical Society in 1970, and they were saving up money to go on this eclipse, and several famous people were on it. Horace Dall, a great optician, was on it. Patrick Moore, of course. The guy that invented the Crayford Mount, John Crow, there was one other one. There were lots of famous people. Norman Fisher, another Croydon person. There were so many people that were involved in that particular cruise, and that's the one where they escaped from Mauritania. They didn't want to go there in the first place, and having visited there in 2013, it's not a lot to see there. There's a fertilizer factory and lots of flies, but they were invited to go around there as we were. I mean, we couldn't get visa to do that, so we couldn't go, which was lucky for us really, because everybody just complained about the smell. But that was the famous junket around the Mauritania and later to the eclipse trip. Edmund Halley. Now, Edmund Halley crops up an awful lot in various things. He was a very famous guy. After all, he was the one that got Edmund Halley got Newton to publish his Principia. And he also had a thing about educating the public. One of the reasons why he worked on comets and their orbits was because he wanted to convince people that they weren't something that just came, or we didn't know anything about them and they went and they caused doom and gloom. They didn't. They were something that could be predicted. And in 1715, he published eclipse tracts for two events that could be seen in England. May the 22nd, 1715, and 11th of May, 1724. The third was an extended map of Western Europe of the May eclipse. And partly that was to reassure the public of this natural phenomenon. It was also because the next part of his job, because he became a follower of the Astronomer Royal following the death of Flamsteed, John Flamsteed, who did the star catalogue, but his part of the job was to map the moon's motions more accurately. In fact, even he couldn't do it very well, and the moon's movements are extremely complicated. So it was part of that as well. But the thing is, this is one of the first examples of an actual track of an eclipse. If you look at modern eclipses in magazines, that's exactly what they show. They show it exactly like that, with cities and towns that are in the eclipse track, and ones that are just outside it, and they give percentages of the eclipse that you're going to see, and so on. So he kind of invented the idea of the eclipse trip. Now, before photography, once people stopped being quite so frightened about eclipses, and let's face it, in the early days they were, they began to notice things about the eclipse, and people began making drawings. Now, that is a really good idea because you can put things down on paper. The real problem, as I found because I tried to do it, is actually trying to draw it quickly is a no-no. It's really very difficult to do. It's just too complex. Now, Etienne Trulot was invited to work at Harvard College. Now, he was a French entomologist. He was an artist, and he was interested in astronomy. And unfortunately, he took something with him to America that he shouldn't have done. He took the larvae of a moth, the snow moth. And unfortunately, when he left America to go back to Europe, he left them with a big problem because it demolished quite a lot of the trees. So in America, he's not particularly thought of highly these days. But this picture of an eclipse looks very fanciful, but in actual fact, it isn't as fanciful as you imagine. And if you get a really good chance to see an eclipse with good equipment, visually, you will see something like that. In fact, I'd seen that picture before, but in 2018, Jan and I went to a very good exhibition at the Science Museum on the sun. And it had everything you want to know about the sun, from sunburn to using it to treat rickets. It was everything, the whole thing. And they did show this picture. And I remember thinking to myself, it's really good because that's exactly what I saw on the 2017 image. It looked like something from an Art Deco poster with these streamers coming out. Also, he drew prominences, which was something that hadn't been done before. And this illustration here is Leslie Ball, who was a BAA member. He produced this image of the eclipse from Gibbons Week in 1927 in England. This picture is from the Observer's Book of Astronomy. If anyone got a copy of that? Unfortunately, probably not now, but I've got to say in the 1960s, it was absolutely it was a really good book. And it had beautiful pictures by him. And this is one of them. He was a very good illustrator, and it showed prominences and the corona, that ghostly pearly white object. Well, the trouble is with illustrations drawn is that they tend to be a bit fanciful. You can't draw them really accurately. That was really difficult because the thing is so awe-inspiring that it's difficult to capture. As I say, I know I tried. I even sent one illustration that I did. I sent it to Stephen. Oh, I can't think of his name. The guy that had Sky Telescope and Astronomy, because he wanted some pictures. And I got a letter back about a year later, a card saying that's really good. But I must admit, it was a very quick sketch. And when I looked at it afterwards, crikey, the corona actually looks much bigger than it should have done. But there we go. Right, photography. Now, photography took a long time to develop. Very good. And here we have the very first one, which is taken by somebody we don't actually know his first name, but Bukowski was his second name anyway. This was July the 28th, 1851. So it's really early. And it's a daguerreotype, which is a technique that doesn't have a negative. It's a very tricky technique to use, but it was the only way that you could do it. And then came the wet palladium plates, and then finally the dry plate in about 1900, where you've got this particular picture. I don't know when this eclipse was taken, but I don't know what eclipse it was, but we could look that up and find out maybe some more details. And finally, right at the end of our period, right at the end of when film was beginning to migrate into digital imaging, we get this particular picture by Patricia T. Espenek. Fred Espenek is her husband. He does all the eclipse predictions, etc. And you can see it's the eclipse of Turkey, and it's beautiful. It's a really good picture. On the other hand, sometimes they would, in early days, they would fiddle. And this one is a retouched version, I'm sure. It says it's from a photograph, and I imagine that that's been somewhat, but that's from 1878. Now, using an eclipse to validate Einstein. Now, we all know that when Einstein released the second part of his theory of relativity, it involved the part about the fact that light is distorted by the presence of mass. Now, we know this today. It's an everyday fact that we know that because we see galaxies that have been shifted by looking towards the galaxies with something in front that's like a black hole or something that's going to really sort of bend the waves, bend the light. But in 1919, it was a very, or certainly 1915, it was a really, really difficult thing for people to swallow. A lot of physicists didn't really believe this. So Arthur Eddington, who was very popular, he did programs on the radio, amongst other things. He's really well known, but he really supported Einstein. He was actually a Quaker, amongst other things. He also was involved with two astronomers, or two people involving Cecilia Payne-Kokoschkin, Cecilia Payne, who came from Wendover. She was one of his disciples, and she went to America, and she was the first person to point out that the real main cause of the stars working the way they worked was through hydrogen. And that was first in America. The other one was Charles Seacar, which he also didn't agree with. The two of them were pacifists, and they didn't agree about his limit and other things. But they were perfectly attuned. They didn't mind that. Anyway, Einstein, what was proved by this eclipse, what they did, they took a picture to a plate of an area of the sky that they knew that the sun would be the site of the eclipse. Then at the eclipse time, he went to Principe, which is just off. The nearest place is Africa, and it's a bit farther east from Africa. And what they did, they pinpointed the stars. And in fact, I think you can see these little markings here on the plate itself that they measured, and there had to be a certain amount of deflection. And it was claimed a success, but it wasn't really. It still fell within error margins. And strangely enough, I was talking about that eclipse of 1973. Well, 1973 was the last time that they did that check again. This was one of the reasons that they used that they're using Concorde and other sophisticated things to take accurate pictures. Whether they did or not, we know it now. It's a fact. We know that it's a fact because we've got pictures taken from the Hubble Space Telescope, etc., that show this gravitational lensing. But of course, in that particular time, it was really something that was right on the borders of the sort of the serious study of physicists. 1930, Bernard Lyell created this coronagraph device, basically putting an objective, a black spot on the center of the optics to block out the sun, and you could see the corona without needing to go to an eclipse. The things needed to be mounted very high up, so you've got water vapor and no dust, and you've got a sort of a semi-result. It was enabled people to see the corona without, so they could see how it changed with time. And of course, one of these changes is really important, as we'll find out in a moment. Spectroscopy. Now, spectroscopy, when it came along, very luckily, it came along at the same time as photography almost. Now, this still is the magic key to astrophysics and a lot of other things, because it tells us so many things. It really was the first. Not only did it show the elements that were present in the sun, but it also showed other things as well. For instance, it showed that sunspots were magnetic. When they took spectra of sunspots aren't really black, they're not really dark at all. They're just a little bit cooler than surrounds. They're about 3,500 degrees K, whereas the surface of the photosphere is around 6,500 degrees K, so a little bit cooler. But it indicated for the first time that the sun is a magnetic body, and when the behaviour of this 11-year cycle of sunspots was sorted out by a guy called Henry SWHAS, who actually studied this for 30 years before he announced the result, that there was actually an 11-year cycle. And that we now know is due to the magnetic fields winding up on the sun and then snapping as the sun is rotating. So we learned several things: that the corona is magnetic, and the sun is largely governed by magnetic properties. Okay. Also, there was the discovery of this area here, which we'll come on to in a moment, actually, of the chromosphere, this very red area that is right on is beyond the photosphere. It's an area beyond the photosphere. But the main thing that it did show was when they began studying the corona, they found that it changed shape, and that shape is changed by the magnetic field strength. you get a different periods when the sun is quiet. You get a different sort of more or less even corona. It's even all around the disk. On the other hand, when it's in a high magnetic state, it becomes much more brush-like. It becomes, the streamers go sideways, which is what you'd expect in a magnetic field. So once you get above the atmosphere, you get spacecraft. Now, one of the problems that we had with the corona is, I said a few minutes ago, that the temperature of the sun's surface is something like 6,000 degrees, 500 degrees Kelvin. The center of the sun is much, much hotter, 15 million degrees. So it's slowly cooling down as it comes, as it passes through the convective layers. It cools down, so that, as I say, the temperature of the photosphere is relatively much lower. Then the chromosphere is cooler still, but then all of a sudden the corona is immensely hot. Now, this posed a real problem for astronomers. They really, how do you know, what's causing that? And I've seen so many articles on this. And in fact, we had the last time we had a talk on the sun, well, in sort of that kind of depth, was by Phil McMahon, who gave a talk in October 2007. And when he was speaking about the corona, he said that mainly this was thought to be to do with the seismic activity of the sun. The sun actually is shaking all the time. It's got actually a regular series of pulses. So, but now we know that the theory, because we're now studying with ultraviolet, all the X-rays, gamma rays, because we're above the atmosphere, you can do this much. And also you can do it continuously and make a movie film of the movement of the corona. But Hans Alpen's 1940s suggestion that magnetized clouds of plasma could carry huge amounts of energy along the sun's field from the core to the corona now seems to be that it is a magnetic channeling that causes this this particular oddity, really. I mean, it's difficult to see. I mean, if anything's connected, you go from hot to cool. Why does it suddenly make that jump? And that is the reason. You've got this really thin, very, very tenuous, but these high magnetic fields and heat being carried from the core of the sun. Then we've got all these developments. The atmosphere strikes back. Now, we've seen a lot of things that you can do with the sun and solar filters. I've got a 1,000 Oaks solar filter that I use on my scope, but that only shows sunspots. But of course, the last 20 odd years have seen a much greater development of HA filters and all sorts of other mimicry and gadgetry that you can get to get a much better view. So we can now see, almost in a sense, much detail as the professionals can. Some of the pictures are really amazing that people take of flaculae, that's flares, and various prominences, etc. In fact, it's got to the stage now, when you go on eclipse, you know what the sun is going to look like. You see, there's going to be a prominence over there, one over there, because somebody's already done that. You know, I sometimes think when you see these people at eclipse sites, they kind of, it's like saying, well, we know who've done it. And if you're going to the going to the cinema and the play, going to the theatre to see the film, the play, The Mousetrap, and somebody saying to you as you walk in, well, I know who've done it. If you want to know, I'll tell you. It's a little bit like that. We now don't have that many surprises. So we get back to the eclipse experience, which I think is most people's sort of experience. Now, sometimes it goes wrong. This was not a success. This really wasn't. We were on a boat in the middle of the Atlantic. We left the Cape Verde Islands. We were heading towards Barbados, and it just came. Well, it was just a horrible day. It was drizzling the whole time. There you can see we've got everything ready here. I've got my camera ready there, and Jan's looking through her dark glasses. But that was what we saw. That was the eclipse. That was it. So not very satisfactory, really. On the other hand, the one that we did to Idaho to see the eclipse was very successful. You'd see people going up this road here. At the end of at the beginning of this road, there's a sign that says there may be snakes in this grass. So you notice people are tending to stay in the middle. Although we did actually venture into looking very carefully where we went. And I think the snakes would have all these people banging up and down. They probably had scarpered long before we got there. And this is the people setting up all their gear. That's Jan and the setup that we had here. That's me looking at the partial phases. And there I am with all the bits and pieces. We took so much stuff up there. I've never seen anything like it. We even had to take our own chair. So it was quite a thing. But on the other hand, we did get some very good pictures. That's one of the opening diamond ring. I've got some others as well. Now the thing is, I'm going to ask a question here. Bearing in mind that today you don't have to go to see an eclipse. You can actually if you look at the sun on the in hydrogen alpha or whatever and see what's going to happen. Then you can look at it on YouTube. Now I just want to do a sort of thing here. Does anybody think that it's really worthwhile going to see an eclipse? So just a brief thing. If that's the situation and you can see it on YouTube, etc., would you go on an eclipse trip? Right. That's what I wanted to hear. I get tired of people saying, we can do it on YouTube. Oh, of course, yeah. It got so bad that Jan and I were walking through Whipsnade a few years ago, and we actually saw a couple showing their children the giraffe, I think it was, by asking them to look in the tablet, and the giraffe was over there. Just jump the giraffe, you know. But reality is much better than something else. Now, when you do a talk like this, they take longer than you think to do, and you do a lot of thinking. Most of the time, it's thinking and scratching your head, which is why I probably haven't got much on top. But you do find that you come up with some things. I didn't want to do that. Where's it gone? Okay, the most remarkable. I wrote this while I was thinking about this. I think the most remarkable thing is that thanks to our ancestors putting aside ignorance and fear, which they had to do, we are able to understand and enjoy one of the most amazing and awe-inspiring sights in nature. And I think that's true. I really do. I think we've come a long way. We've still got a long way to go. And I want to tell you that we're still frightened of the dark, because when there was an earthquake in Los Angeles, I believe it was back in the 90s, people were frightened because they could see the Milky Way. They didn't know what it was. And they actually were really frightened because they thought it was something coming to get them. So anyway, let's go on to the next one now, and we should come up with questions.
Okay. I saw the eclipse in '99, actually. I was in France, and I was in the middle of a field. It was a beautiful day. And I remember it was still bright up until the very last second almost that the moon went in front of the sun. And they say that you're not supposed to look at an eclipse with the naked eye, but bearing in mind that you can look at the sun, although it hurts your eyes when it's a full sun, not for very long.
Yeah.
But when the moon goes over the sun, it cuts the light by about 99%. Does that really hurt your eyes, or all these glasses? Is this a myth, or is it a fact? Is that the question?
No, it shouldn't do. I mean, the thing is, you shouldn't gaze at the sun. But I mean, obviously, when you get the last fractions of the sunlight, it's still the same brightness. It's just that there's not the whole disk. So, I mean, theoretically, if you stared at it, you would damage your retina. But a glimpse is not going to do that, because we all do it. And it really isn't. Once you've got past that, then it is safe. I mean, it's not. But I know there's a lot of controversy about this. But there was an article quite recently in Astronomy, and but that, you know, we overemphasize it. I mean, the sun's dangerous, whether it's an eclipse or not. It's not that it's looking at it is not a good thing to do, but you can do occasionally glance at it. And if you're going to do that, well, that's not going to damage your retina, because you're moving your eye about. You're not sort of sitting in one spot. So it's not the image is not focused on one spot of your retina.
Yeah, we at the moment we happen to live in a time when the moon is exactly 400 and the sun is 400 times larger. Goldilocks time, if you like, from a solar eclipse perspective.
Yeah.
Obviously, with the moon moving away, at some point, we will no longer have eclipses. And I'm assuming that's a long period, like a 10 million or 100 million plus high time frame. Do you know how long before we will lose
Well,
eclipses?
Funnily enough, there was in a question and answer thing some years ago, somebody asked that very question, because you're quite right, the moon is moving out roughly 3 feet every century, is moving away, but it won't actually, it really doesn't matter in a sense, because it's going to be before the sun will have changed before that happens. So the sun's going to obviously change, and it won't, it's going to expand and get hotter. So for the light as the sun is now, and we've got quite a long time yet. So I could almost say, and I don't like to be pessimistic, but it probably will outlast the human race, because by that time the Earth won't be habitable. So I think we're safe at the moment. So you can go on the one next year or whenever it is, and we'll be all right.
Have we got any other questions?
From the moon's point of view, does the Earth eclipse the sun? If the alignment is such that if you were on the moon, you would see a total eclipse of the sun by the Earth?
That when the moon is in eclipse, in other words, when the moon's in the Earth's shadow, you see the sun's light all around the globe. Yes, in that sense, I'm not quite sure what you're trying to suggest, or what your question is, I'm afraid. Because in that sense, that's the other way around. If you have the sun, Earth, and moon, the moon is on the other side. So, and the Earth is eclipsing the moon. From the Earth is eclipsing the sun from the moon.
Yeah.
Is that what you're?
Yes, that's right.
Yeah. Well, in actual fact, that we do see that every total eclipse of the moon, because what happens is that the moon is a much bigger body, so it shields the sun quite, completely out of many times. So what you do see is a ring around the Earth, which is all of the sunsets of the Earth and sunrises around the Earth. It's a ring of red light. So that's the equivalent in a sense.
Yeah,
that's the best way I can explain it.
Yeah, yeah.
Right. Okay, so we're now going to move on to the second part, which is what's up in the sky tonight. Now, one of the things that we're losing now is, of course, the summer sky. But at the moment, we have several rather interesting planets around. Now, I'm sure most people will have noticed that we've got a planet in the early evening sky and one in the later sky. First one is Saturn. Let's get rid of these labels. Don't really need that. We know where we are. There we go. Saturn is at the moment in the west, immediately after sunset. Or rather, it's in the south. Later on in the night, it moves to the west. It's past opposition by several months now. It came to opposition in August. So what we're actually seeing now is a little bit. We're seeing slightly to one side of Saturn, and we're actually seeing the globe with the shadow of the globe crossing the rings. And I've said before, that little notch out gives you a much more sort of 3D view, I think. I had a look at it the other night. I had Bonanza. I looked at 4 planets in one evening, which is a long time since I've done that. But Saturn was my first port call. Now, unfortunately with this, you can't zoom up on this. Can you just have a look? Do it another way. No, you can't. Okay, I'll try that again another time. It worked on my one at home, but it doesn't. This hasn't got a roller situation that you can glide. Yeah, now you can see the rings of Saturn, and sorry about the glare around it, but it will eventually reveal planet. But yeah, just to show it can be done, and I'll do the same thing with Jupiter, and I think we'll call it quits after that. It's a bit slower than I thought. Jupiter, that's Jupiter. And Jupiter, bright planet, is actually you could see it. I noticed it at sunset this evening. There, brilliant. Saw last Wednesday. I could see the shadow transit of Callisto as it crossed the planet. Worth looking at. Watch the satellites. Quite a lot of activity on Jupiter at the moment, including the Great Red Spot, of course, which is the thing that. See if I can do this again and make it a bit more. Oh, we know what Jupiter looks like, don't we? I hope. Now, the other planet I wanted to point out, which is in our sky at the moment, is is actually Mars, which is down here. Mars is at the moment quite bright in the evening sky, late evening. In fact, I mistook it for Betelgeuse. I thought it was Orion arising, and then eventually got too bright for that. And I had a look, and it is Mars. I did have a look at Mars on Wednesday evening. And I couldn't see any detail. Now, admittedly, with a very small telescope, 4-inch short focus scope, not going to see an awful lot. But I couldn't see any. It looked rather yellowish, and I wondered if there's a storm, dust storm in progress. Could be. I don't know. If somebody does imaging, etc., and they want to have a look, let me know. I'd greatly appreciate that, because it's really good. That's what I like to hear. If anybody does images of the planets, they're very handy for us people that look at them to see what we're seeing, to kind of marry them up, because sometimes you were just working in the dark. So that's it for this evening. I think the universe is definitely condensing down. I think we must have discovered the collapsing universe there, getting it all into a bubble. Maybe some cosmologists will write an article on that. Okay, well, thanks very much, everybody.
Thanks, Richard, very much. Well, that wraps it up for this evening. So thank you very much for attending and your patience and waiting for us to start and everything else, some of the problems that we've had. But hope to see you next time. And in the meantime, enjoy the refreshments. Thank you.